Okay, so this is the exam to review. I'm just gonna go through the study guide that she gave you guys. Alright, so number 1 on the study guide, it says determine the charge of the polyatomic ions. So in each of these compounds, we're gonna look for the polyatomic ions and try to decide the charge. So in this first one, you can see the polyatomic ion ammonia, and it's attached to an oxygen. So all we need to do is determine the charge of the thing that it's attached to first. So oxygen, we know, has a charge of -2 based on its position on the periodic table, right? So then looking at the ammonia, this whole thing has to have a charge of +2 in order to balance the compound, since there's no overall charge. The overall compound is neutral, so the charges have to balance. So if it's +2 and there's 2 ammonia molecules, each one of them has to be +1. So the NH4 in this molecule, each one has a +1 charge. Or if she's asking you the total charge, that would be a +2 charge. So just read the question carefully and decide your answer based on what she's asking you. Okay, and then moving on to the second one, we have the polyatomic ion hydroxide. It's attached to the sodium atom, and we know based on the position on the periodic table, the sodium atom has a +1 charge. So we're going to find the charge of the atom that the polyatomic ion is attached to. And then since that one's a +1, this ion has to be -1 in order to balance, since this compound is neutral. So the OH has a charge of -1. Alright, and then moving on to number 2, she says select the correct formula for sodium phosphate. So this is just an example of polyatomic ion that I made up. So she said in the question that she's going to give you a hint, I think. So I assume she's going to give you like the charge of the polyatomic ion. So based on the charge, phosphate has a -3 charge. You can see that here. So all you have to do is balance it. Kind of what we did in the beginning, just backwards. So now in this question, we know the charge of the polyatomic ion. And we have to... just realized these are potassiums. Let me cross this out. Okay, potassium phosphate. Okay, so we have a phosphate ion that has a charge of -3. We know that based on the periodic table, potassium has a charge of +1. So in order to balance this and make it +3, we have to have 3 potassiums. So if we do +1 times 3 potassiums, that gives you +3 charge. So the answer is going to be C. So this question, you just have to know the charge of the polyatomic ion, and I think she said she's giving you that. So that one should be pretty simple. I'm going to move on. Okay, this one says name the compound containing a polyatomic ion I came up with H2PO4, and it says hint provided. So I'm thinking that means she's going to give you the name of the polyatomic ion. So this one is phosphate. And if she gives you that, all you have to do is figure out the name of this part of the H2. So we know for covalent compounds like this one, there's no metals here. These are all nonmetals. So we know it's a covalent compound. We're going to have phosphate at the end. So we already can rule out C. So the name of the polyatomic ion comes at the end, not the beginning. And then between A and B, we either say hydrogen or dihydrogen. So in an ionic compound, you wouldn't have the prefix in the front, but because this is covalent, we're going to have that di prefix. So it's going to be letter B. Okay, moving on. So we're going to indicate ionic or covalent compounds. So let's go through each one of these. Just want to make sure that was still recording. Okay, so this one, we have a metal. This is just based on the periodic table positions. We know that sodium is on the left side of the periodic table, so that's a metal bonded with a non-metal. So metal plus non-metal equals ionic bond. So this one is ionic. Here we have another metal of calcium, which is also right on that left side of the periodic table. It's bonded to this carbonate polyatomic ion made up of all nonmetals. So again, that one's a metal plus a nonmetal, so that's going to be ionic. This one here is carbon dioxide. It's made up of a nonmetal and a nonmetal. So those are both on the right side of the periodic table. So those are both nonmetals, so that's going to be covalent. And then this last one is another metal with a nonmetal. We got lithium and oxygen. So this one is also going to be ionic. Okay, I'll highlight that. Okay. Number 5 says select a diatomic element. So these ones are just kind of ones you have to remember. It's these 7 down here. It forms a 7 conveniently over here on the left or right side of the periodic table, and also this one, also hydrogen. So you just have to memorize this. Unfortunately, it's nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and hydrogen. So of these options, it's going to be letter C. It's going to be H2. So diatomic just means that the element exists in a state like this. Like there's 2 atoms attached to each other. You wouldn't just find like one hydrogen atom in nature. It's always H2, N2, O2, F2. Oops. So these ones all naturally exist in pairs of 2. Okay. And then this one says select the formula. I think for covalent compound is what the question said. So I just made up this one, dichlorine heptoxide. So chlorine, we know Cl, oxide is oxygen. And then looking at the prefixes, we have dichlorine. So you know that's 2. and then heptoxide, hept equals 7. So it's going to be letter B. So we have mono, di, I don't know exactly how far she's going to go out. I would assume not any farther than 8, which is oct down there. So it's 1, 2, 3, 4, 5, 6, 7, 8. We have mono, which is 1, di is 2, tri is 3, tetra is 4, pent is 5, hex is 6, hept is 7, and oct is 8. So another thing you kind of just have to remember, but I don't think she'll go probably any farther than like 5 or 6 probably. Yeah. Okay, and then for this question, we're gonna do, let me draw just a random molecule. Let me do this instead. Okay, so this is HCN. So this is going to be bond A and bond B. So it says how many shared electrons are in bond. She might have like a molecule drawn out like this and have the bonds labeled, I would assume. So looking at bond A, we know that in a single bond, there are 2 shared electrons. In a double bond, there's 4. And in a triple, there's 6. So for each line, there's 2 shared electrons. So in bond A, there's going to be 2 shared electrons. In a triple bond, we have 3 lines. So 2 electrons in each line is going to be 2 times 3 equals 6. Okay, so bond A has 2 and bond B has 6. Number 9 says, what is the difference between bonding and non-bonding electrons? So this one's not a multiple choice question. I just wrote some information that I think would be helpful for this question. Oops, this is supposed to say bond. Okay, so bonding electrons are always shared. They're contained in a bond, like this. These are bonding electrons. Non-bonding electrons are not shared, so they're usually in a lone pair. So they might look like this. These would be non-bonding because they're not contained in a bond. Okay, and then also bonding electrons are valence electrons usually. So on the outer electron shell. So like if we go back to what we know about the periodic table columns, an example would be like nitrogen has, 5 valence electrons. But we know that it has more than 5 electrons. Its atomic number is, I actually don't remember. Let me look it up real quick. Okay, nitrogen's atomic number is 7. So that means it has a total of 7 protons. So it must also have 7 electrons. So it has 7 total electrons, but it has 2 of them are core electrons, which means they are in that shell that's like closest to the nucleus, where we have 5 out here. So the bonding electrons are going to be the ones, the valence electrons that are on the outer shell, because they're not as closely attracted to the nucleus as the other two. They're also just like out there. They're more accessible for other atoms to come along and form bonds with. So the non-bonding electrons are core electrons. Those ones don't participate in chemical reactions. They are just hanging out inside there. Okay, I just put 10 and 11 together because I'm not exactly sure what kind of question she's going to ask. So I just put some more information. So periods go across the periodic table horizontally. So looks something like this. So periods go across like that. And groups go down, up and down the columns vertically. So group are going to go up and down like that. So she might ask you something about like electronegativity trends. We know that electronegativity increases left to right. So it increases left to right across a period. And it increases bottom to top across a group. Right? Okay. And then also the valence electrons is based on the group number, right? So we know that, oh, there should be another one. Oops. Okay, so going across the periodic table, the group number is going to be 1, 2, and this isn't accurately drawn, obviously, but it's going to go 1, 2, 3, 4, 5, 6, 7, 8, something like that. So we're going to skip this transition metal part. We're going to do the 2 columns that are over here, 1, 2, and then continue over here. So it's going to go 3, 4, 5, 6, 7, 8 as you move across the groups. Right, so like everything in this first group is going to have 1 valence electron. And then that trend continues across. So everything in this group will have 2 valence electrons. So just some things to keep in mind regarding periods and groups. Okay, and then moving to question 12. It says determine the number of valence electrons in a molecule. So we're going to use what we just talked about in the last question. So we're just going to add up the number of valence electrons per atom. So nitrogen has 5 valence electrons based on its group number. It's in group 5 up here. So we know it has 5 valence electrons. Hydrogen is in group 1, also up there. So it's going to have 1 valence electron. But there are 3 of them. So we're going to do 1 valence electron for every hydrogen atom. So 5 plus 3 equals 8. That's going to be letter C. So you're just going to do that one, or just do that process for each question. Just line it up with the group number on the periodic table and add them up. Okay, so this one says how many multiple bonds exist in a compound. So again, in NH3. So for this question, we're probably going to have to draw the Lewis structure, just so we can visualize the number of multiple bonds. And this refers to like double bond or triple bond. So we're going to start with the central atom. It's going to be nitrogen. And then add the surrounding atoms. We just said that it has a total of 8 valence electrons. So then we're going to add the bonds to each surrounding atom. So in each of those bonds, there's 2 electrons. So we just used up 6 of them. So we did 3 bonds, each with 2 electrons. That's a total of 6. So we have 2 electrons left over that we have to add. So we're going to look at the central atom. It's only got 6 electrons in its valence right now. So we have to get it up to 8. So what we can do is just add a lone pair. That will take care of the 2 electrons we were missing. And now every atom has the right electrons in its octet. The nitrogen has 8, and each hydrogen has 2. Okay, so now that we're done with the Lewis structure, how many multiple bonds exist? So in this one, there's 0. There's only single bonds and lone pairs. So, no pi bonds. Okay, and then the next question says how many non-bonding electrons exist in a compound. So again, we're going to need the Lewis structure for this question. We already drew it up there. So non-bonding pretty much only refers to lone pairs. So these electrons are all bonding electrons because they are within a bond. We're looking for these ones that are not within a bond. So we got 2 here. Whoops. That's going to be letter B. Just look for the number of lone pairs, count the number of electrons. There's 1, 2. Okay, this question says you're going to need to select the best Lewis structure for a given molecule. So let me just draw some real quick. We already know the answer for this one, but she's probably going to give you a couple of different Lewis structures. There's going to be probably, I imagine, something wrong with each one, except for the correct one. So she might give you some options that look like this. They're all similar, but have little differences. So this first one, letter A, looks like the right answer, but we gotta check the octets. So each hydrogen is satisfied. They each have their 2 electrons in the double bond. They each have their 2 electrons in the single bond. So remember, hydrogens have a duet, not an octet. Whoops. So they only need 2, not 8. So in this first one, each hydrogen is satisfied, but the nitrogen only has 6 instead of 8 in its octet. So this one is not going to be the right answer because the nitrogen does not have enough electrons surrounding it. Whoops. that's why earlier we had to draw this lone pair in order to satisfy the nitrogen and have 8 electrons surrounding it. So we already know that one's the right answer because we drew it up here, but let's just go over letter C. In this one, the nitrogen is satisfied. It has 2, 4, 6, 8. However, this hydrogen now has 4 electrons. So that's too many. The hydrogen can only have 2. So because it has 4, that one is incorrect. It would not exist in nature. That one is also out. So just gotta look for little differences like that. So check octet/duet. Check number of atoms. She might give you something like this, maybe, where it only has 2 hydrogens. So that one can't be right because it's not the same molecular formula. So just look for little things like that. Number 17. Moving on to chapter 4 now. So this one says determine the difference between electron geometry versus molecular geometry. So this one again, just providing some information that might be helpful. Electron geometry is determined by the positions of the electron groups in the molecule. Molecular geometry is determined by the positions of the atoms in the molecule. So an electron group, remember, is a lone pair or any type of bond. So if we had something like this, the number of electron groups here is 1, 2, 3. So it's, even though there's 2 bonds in this double bond, it still only counts as 1 electron group. Or if we had, just go back to our ammonia example. This one has 1, 2, 3, 4 electron groups. So even though this lone pair is not a bond, it's still an electron group. And even though it has 2 electrons, it still only counts as 1 electron group. So we need a lone pair, which refers to 2 electrons, or any type of bond, single, double, or triple, right? Okay. So the next question says, why do atoms arrange themselves as far apart from each other as possible around the central atom? So the answer to this one is just that the electrons in the bonds repel each other, all with equal force. So if we have an example like methane, there are 2 electrons in each bond here. Let me draw that more clearly. Right? There's 2 electrons in each bond. They are all negative. They all have a negative charge. So these negative charges will repel each other. So each, kind of envision it like that, like each electron pair is repelling each other with the same amount of force. So if they're all repelling each other with the same amount of force, they're all going to be in equal distance apart from each other. So these ones are going to be kind of like at a 90-degree angle. You could do, so boron 3 electron groups. So all of these groups are going to be the same angle away from each other. I think it's like 109.5 or something like that. So since they're repelling each other with the same force, they're all going to be the same distance away from each other, if that makes sense. Okay, next question says identify the electron geometry for given molecule. So in this one, you're going to have to, I'm not sure if she'll give you the Lewis structure or if you'll have to draw it, but either way, we already did this one earlier, so we know it looks like that. So electron geometry, counting the number of electron groups. So we just did this one a second ago. We said it had 1, 2, 3, 4. Let me make that more clear. It's counting a number of electron groups around the central atom. So if there were to be lone pairs over here on these surrounding atoms, we don't need to think about those. We're only looking at the ones on the central atom. So all you have to do is just count them. So we said there were 4. Looking at that chart that she gave you with like the electron and geometry. Let me see if I can pull it up. Actually, just a second. Let me find one real quick. Okay, so looking at this one, we're going to start on that first column on the left side. It's the number of electron groups. And then moving over to the second column, we had 4 electron groups. So the one that corresponds with 4 electron groups is called tetrahedral. You can see that there. So this one is going to be tetrahedral for electron geometry. And then if we look at the molecular geometry, same Lewis structure. This one is going to be based on the number of electron groups and the number of lone pairs. So going back to the chart, if we look at that second column, we're still in electron pair geometry, still tetrahedral. And then moving over to that molecular geometry column at the top, it says no lone pairs, 1 lone pair, 2, 3, or 4. So our molecule has 4 electron groups. And then if we follow over into the 1 lone pair column, it says trigonal pyramidal. So our molecule has 4 electron groups, one of which is a lone pair. So we're going to use the table. I don't think you'll have this table on the exam, so you will have to memorize this. But yeah, we have 4 electron groups, which means it's tetrahedral electron geometry. One of those is a lone pair, which means it's a trigonal pyramidal molecular geometry. If it had 2, it would be called a bent molecular geometry. So let's go back here. We got 1, 2, 3, 4. We we got 4 electron groups and 1 lone pair. So that means it's going to be trigonal pyramidal. If we had a different example, looks like this. This is an H2O molecule. It's got 1, 2, 3, 4 electron groups. But this one has 2 lone pairs. So it's going to be the same electron geometry. It's still going to be tetrahedral because it has 4 electron groups. But the molecular geometry will be different because of the different amount of lone pairs. So going back to the table, we're at tetrahedral still. We still have 4 electron groups. Then going across that table all the way to 2 lone pairs. That one's called bent. So if you were to be asked what's the molecular geometry of H2O, that one is bent. Alright. So number 21, a molecule contains a central atom. I think this one said determine the molecular geometry based on the number of bonds. Let me look at it again. Okay, so this one, I don't think she'll give you a picture or a molecular formula. You just have to kind of picture it in your head. So if we're looking at electron geometry, we're going to be looking at number of electron groups. So just based on how it's described, it has 1 double bond, 1 single bond, and 1 lone pair. So these are all electron groups. A double bond is 1 electron group. A single bond is another electron group. And a lone pair is a 3rd electron group. So going back to the chart, we're only looking at that second column right now. We're not worried about molecular geometry yet. It's got 3 electron groups, so that means it's going to be a trigonal molecule. The electron geometry is trigonal, or not sure how she'll word it. It can be called trigonal or trigonal planar. So we can remember that because it has tri at the beginning. It's got 3. That means tri. Okay. This one says define electronegativity. So electronegativity is an atom's affinity for electrons within a bond, or its tendency to draw electrons toward itself. So if we had a bond like this, the fluorine, we know based on the periodic table trend, it's farther to the right on the periodic table. So that means it's going to be more electronegative. The electrons are going to be drawn towards the fluorine because it has a higher tendency to draw electrons toward itself. So, yep, and then also increases left to right, increases bottom to top. This is a poorly drawn figure, but yeah, so it increases this way, increases this way. So if you had something down here versus up here, this one would be more electronegative. Okay. So this question, she's going to give you a couple different options for the correct dipole illustration. So let me just draw some of those out. Okay. change this to incorrectly. So select the one that is not correct. Okay, so looking at these ones, we're always going to draw the dipole arrow from, okay, the less electronegative, I'm going to abbreviate that EN. So the plus sign part of the dipole is going to start at the less electronegative atom, and the arrow is going to go towards the more electronegative atom. So looking at HCl, this one is more electronegative because it's farther to the right on the periodic table. So this arrow is correct because it's going towards the chlorine. Okay, and then the second one, this one is also correct because the fluorine is pretty much the most electronegative atom there is, really. So if you see a fluorine, that one is probably always going to be more electronegative than whatever it's attached to. So it's going towards the fluorine. That one's all good to go. Now this one, a CH bond. The problem with this bond is that it's, this one is non-polar. So there can't be a dipole arrow because there's no dipole. There's no polarity difference. Well, there is a small difference, but not enough to be considered a polar bond. So this bond is non-polar. So there should never be a dipole above a bond, a CH bond, because there's no dipole there. So this one is incorrect. Okay, moving on to this question. She's going to give you a molecule and ask you if it's polar or non-polar. So looking at CCl4, we've seen this one before. It's a carbon with 4 chlorines on each side. So this one is going to have 4 dipoles that are all equal. They're all the same bond. They're all a carbon single bonded to a chlorine. So we know that they're all equal. They're all pointing oppositely from each other. They're all the same exact type of bond. So this one's going to cancel with this one. This one will cancel, with this one, leaving you with 0 net dipole. So this one is going to be non-polar. Even though each individual bond is polar, they cancel each other out. And then CH4, this one, you don't even have to worry about dipoles canceling out because there are no dipoles, right? There are very small dipoles, actually, like this, but they are not, based on the chart that we were given, the dipole is not enough to be considered. The electronegativity between carbon and hydrogen are so close. They're different, but they are so close that the difference is kind of negligible, like we don't need to worry about it. So these bonds are all polar bonds. I'm sorry. These are all non-polar bonds. So this one's also going to be non-polar. And then the HCl looks like this. So the dipole is going from the hydrogen to the chlorine. And in this molecule, there's nothing to balance that dipole. There's nothing on the other side that's gonna balance it out. So this dipole is just straight across. So this one is gonna be polar. So you have the partial positive over here, partial negative over here. And there's no canceling out. So that one will be polar. Okay, looking at this one. What type of intermolecular forces are attracting the molecules together? So the options I think we have are only dispersion, dipole, or hydrogen bonding. Okay, so looking at the CH4, we just said up here that the CH4 is nonpolar. All of the bonds in those molecules are nonpolar. So in this question, you can kind of think of, I'll just write it like this. A bunch of CH4 molecules floating around together. So the question is asking what type of intermolecular forces are attracting the molecules together within like a container. So this one, you can kind of just connect nonpolars with dispersion forces. So because all of these are nonpolar, there's nothing really attracting them together except the fact that they're close together. So dispersion you can associate with nonpolar, because these other two require dipoles, right? So if you have something that's nonpolar, there's no dipole. So it can't be dipole or hydrogen bonding. Okay, and then looking at HCl, we just set up there that this is a polar bond. So if you have a polar bond, you're deciding between dipole or hydrogen bonding. So in this one, there are specific rules that you have to remember with hydrogen bonding. So a hydrogen bond is polar, but it has to be between a hydrogen and an oxygen, hydrogen and a nitrogen, or a hydrogen and a fluorine. So everything that's not an oxygen, a nitrogen, or a fluorine, that is not considered hydrogen bonding. So let's go back to HCl. So this is a polar bond, we said. Right? It has that dipole between the hydrogen and the chlorine because the chlorine is so much more electronegative than the hydrogen. So if you had a bunch of these together, right, the hydrogen is partially positive, the chlorine is partially negative. So that means that the hydrogen and the chlorines are going to be attracted to each other because of their opposite charges. Right? Because one of them, because the electron density is being pulled towards the chlorine is going to be slightly more negative than the hydrogen. So the partially positive hydrogen of one molecule is going to be attracted to the partially positive chlorine of another molecule. And that's where the intermolecular term comes in. It's between two different molecules. So this one is going to be dipole-dipole, because the dipoles of each molecule are attracted to each other. And we know it's not hydrogen bonding because this is a hydrogen attached to a chlorine. It's not attached to an oxygen, nitrogen, or fluorine. So then looking at H2O, this one's going to be very similar to dipole-dipole, except it's special because it's a hydrogen attached to an oxygen, which is one of our conditions. So these three are just ones you have to remember. So on this one, it's going to be the same. The hydrogen is partially positive, the oxygen is partially negative. So the hydrogens are going to be attracted to the oxygens of the other molecule. Like this. Right, so the oxygens of one water molecule are going to be attracted to the hydrogens of another molecule. So very similar to dipole-dipole. Actually, it is a dipole-dipole bond, but it's also more specifically a hydrogen bond because, or I should say dipole-dipole interaction, but more specifically it's a hydrogen bond interaction just because of these three conditions. So this one is hydrogen bonding. Okay, so those are the rules you can remember. Dispersion is associated with nonpolar, dipole-dipole is with polar, hydrogen bonding is polar, but if it's any of these three specific bonds, then that's how you know it's hydrogen bonding and not just dipole-dipole. Okay, moving on. This question says, what does not occur in a chemical reaction? So the four options are color change, production of odor, bonds are broken or formed, or new elements are created. So these two we can rule out right away because we know that color change and odor production are both indicators of a chemical reaction as opposed to like a physical change, right? Like a state change, like melting or something like that. So bonds being broken or formed, this one is an indicator of a chemical reaction. Oh, let me not circle that. Yeah, so this one is an indicator of a chemical reaction, new bonds being broken or formed. So if we had like this, so in this reaction we had a bond here, but it was broken and a new bond was formed between the sodium and the hydroxide. So that's an example of that. So the last one says new elements are created. So this one is referring to like the difference between a chemical reaction versus a nuclear reaction, like we talked about earlier. So this one would be like uranium turning into, I can't remember exactly which one comes after uranium, but those ones we did earlier where the atomic number changed, so that would turn like a uranium into something else. In this case, I just put radon. So this one indicates a nuclear reaction, which is different than just a chemical reaction. So this one is not a chemical reaction. See, like this one, the bonds changed, the bonds broke, and new bonds formed, but there was no new elements formed. There's one sodium, one chlorine, one chlorine. And this one's kind of tricky. You would have to balance the equation, but there's oxygens, hydrogens, oops. But you can see, like, there's no new elements that were formed, no new atoms. It's all, like, balanced on both sides. So a nuclear reaction creates new elements, like this one to this one. Okay, number 27. This one's going, oops. I meant to say chapter 5, not 25. Anyway, so this one just says select the correct match of molecular formula to molecular mass. So this one should be pretty simple. This is like what we did in the chapter 3 question above. We're just adding up the number, I think that's not right. Yeah, we're just adding up the molecular masses of each atom in the molecule. So this one, nitrogen has a molecular mass of 14.011, I think, or something like that. Hydrogen has 1.008 grams per mole. So if you add those up, it's close. I think I rounded, but if you add them up, it comes out to be 17 point something. You should do that on your calculator just to make sure, but you're just going to look at like the number below the atomic symbol. So this one on the bottom is going to be the molecular mass. You should have a periodic table to refer to. So you're just going to add those up. Oh, I forgot a step. This one is going to be multiplied by 3 because there's 3 hydrogens. So it's going to be 14 roughly plus 1 times 3 equals about 17. So this one is correct. These other ones, if you do the same thing and add them all up, add up 2 hydrogens plus 1 sulfur, that comes out to be around like 35 point something, I think. So this one's incorrect. This one's also incorrect. It should be like, I think 180 something for glucose. So yeah, for these ones, you just have to add up the atomic masses of each atom and make sure that they're correct. Okay, 28 says, what is the difference between the molecular mass and the molar mass? So this one, I'm not exactly sure how she will ask this question, but as far as I know, the molecular mass and the molar mass are the same value. So like we just said, like nitrogen has a molecular mass of 14.011, I think, or maybe it's something close to that. So the molecular mass, like I said that backwards, but the molar mass is 14.007 grams per mole. And I think when we're talking about molecular mass, the only difference is that you would say it in AMU, or atomic mass units. Oops. So it's the same number, just with different units. I'm not sure how she will ask that question, but that is the only difference I can think of between those two terms. Okay. Number 29 says, determine how many atoms are in a given number of moles. So this one we have to use the relationship of Avogadro's number, which is 6.022 times 10 to the 23rd atoms per mole. Okay, so we're going to start with what we're given. We are given 3.03 moles of NH3. We're going to have to use a conversion factor to get from moles to atoms. That is going to be right here. We have a relationship that relates moles and atoms. So we want moles on the bottom so that we can cancel moles with moles. So that means the atoms is going to have to go on top. So moles is being canceled. We're just going to multiply that number. Let me get a calculator. That comes out to be 1.82 times 10 to the 24th atoms. So for that one, if you're going from atoms to moles, or moles to atoms, you're going to be using Avogadro's number. I'm not sure if she'll give you this number or not, so I would just memorize it. 6.022 times 10 to the 23rd atoms per mole. Or in some cases it might be molecules per mole. Actually, this one should be molecules because this is a molecule. Let me... So it's the same thing, just if you're like, if I had asked like 3.3 moles of like aluminum, that is one element, one atom. So that's why I would say atoms. But this one says NH3, which is a whole molecule. So that's going to say molecule instead. Same thing, just different word. Okay, number 30 says how many moles are in 6.056 grams of sodium chloride. So grams to moles or moles to grams. We're going to be using the molar mass. So we're going to start with what we're given. We're given 60.56 grams of NaCl. So the conversion factor is going to be the molar mass that is in grams per mole, right? So for this one, we're going to have to add up the molar mass like we did in this question. So the molar mass of sodium, let me look that up real quick. It's about 22.99 plus the molar mass of chlorine. It's about 35.45. So adding that up, the whole thing equals 58.44 grams per mole. Alright, so now that we have that conversion factor, you have to decide what's going on the bottom versus what's going on the top. So we're starting with grams. So we want to have grams on the bottom so that we can cancel it and be left with moles, which is what we're looking for. So we just have to multiply 60.56 times 1 over 58.44 that gives me 1.04. Since we have 4 suffix here, I'm going to go out to 1.036 moles. Okay. So those ones are pretty simple. We just have to use one conversion factor. So this one is a little bit trickier. We're trying to go from mass all the way. Actually, we're going to be starting with number of molecules. I'm trying to get to mass. We can't really do that though because number of molecules is in molecules per mole and mass is in grams. So these two factors don't relate to each other directly. We're going to have to go from number of molecules, which is in molecules per mole, to moles, which is in grams per mole, to grams. So we can't go straight here. Have to go here and then here. So let's write that out. This is just information that we can use just so we don't have to calculate the molar mass because she said she would be providing it. So that's not actually where we're starting. This is just extra information that we can use. We're going to be starting with the number of molecules. So this is just a conversion factor that we're going to use in the middle of the calculation. This is like an actual value that's being given. So we're starting with this given value of 2.11 times 10 to the 22 molecules. Oops. So we're starting with molecules. So the only conversion factor we have that includes molecules is Avogadro's number, right? Because that can be either atoms or molecules per mole. So if we want to cancel molecules, we're going to put 6.022 times 10 to the 23rd molecules on the bottom, 1 mole on the top. This is going to be canceled. Now we're left with moles. But we want to get to mass, which is in grams. So we just went from molecules to moles. So we just did that first step. We went from molecules to moles using Avogadro's number. Now we're going to have to combine steps. So now this is all set. Now we're going to go moles to grams, which is what we just did in number 30. And the conversion factor we had to use was molar mass, right? So we used Avogadro's number first. Now we're going to have to use molar mass. And that was already provided. So all I have to do is set up a conversion factor. So we want to cancel moles and be left with grams. So we're going to put moles on the bottom. Put grams on the top. So that means moles going to cancel. We're going to be left with grams, which is what we wanted. Scoot this over. Okay, so now all we have to do is go through and multiply. So 2.11 times 10 to the 22nd times 1 over 6.022 times 10 to the 23rd times 110.98 over 1. That gives me 3.8. Let me see the sig figs. The smallest number of sig figs is in 2.11. That's 3 sig figs, so we're going to do 3.89 grams of calcium chloride. Okay. So this one is just combining two steps, going molecules to moles, or atoms to moles, and then moles to grams. Alright. And then the last question. The question says, which has the greater mass if you have 1 mole of 2 different molecules? So this one, all you have to do is just add up the molecular mass, like we just did in number 30. So molecular mass of nitrogen is 14.007 plus hydrogen is 1.008 times 3 because there's 2 of them, or 3 of them. That's gonna equal 17.03 grams per mole. So this is the molar mass. And then for H2S, it's gonna be 1.008 times 2, because we have 2 hydrogens, plus the molar mass of sulfur, which is 32.065. And you can find those again on the periodic table. Underneath the atomic symbol. Okay, so adding those together is going to equal 34.1 grams per mole. So because we have an equal number of moles of each of these, you don't really have to even worry about that. You're just going to compare the gram number, because we're looking for mass. So if you have the same number of moles of each one, then all you have to do is compare the grams. So this one has a higher mass because it has 34.1 grams per 1 mole, versus the other one only has 17 grams per 1 mole. So if you have 1 mole of each, then you have 17 grams of one and 34 grams of the other. So this one is going to have the greater mass. Okay, and I think that was all. Good luck tomorrow. I hope it goes well.